in progress.
All right, guys, so we are going to go ahead and start on Unit 5. This is our nomenclature unit. This is looking at how we name compounds and write formulas for compounds. There are going to be kind of sets of rules that we have to follow, and this might be different depending on if it is an ionic compound or a molecular compound. So that's one thing that you're going to have to pay attention to as you go through the unit is what type of compound are we dealing with. So we're going to start off with ionic compounds. These are what we tend to deal with the most, simply because, remember, ionic compounds do contain a metal and a nonmetal, and most of our elements are metals. So we tend to deal with ionic more often than anything else. So before the science of chemistry was developed, how they would name compounds was based off of their properties or what they did. So for example, N2O would make people laugh whenever they breathed it in. So it was referred to as laughing gas. There might be a gas that would make you fall asleep. So it might be considered sleeping gas, things like that. However, with performing experiments to show how different compounds can be formed, we figured out that there's too many different names and too many different things to memorize. So it was almost impossible to memorize all of those common names of compounds. So the French chemists developed a new method to name these compounds, which is what we use today. So we actually name them based off of what they're made of versus what they do. So we first want to look at how we name individual ions, and we're going to put the ions together to name compounds. So we are going to start off with monatomic ions first. Mono means one. So this is a single atom that has a positive or negative charge from either the loss or gain of a valence electron. So these are going to be how we name our cations and how we name our anions. And remember, valence electrons, the ones that are bonding, are the electrons in that outermost energy level. So let's look at the cations first. Remember, these are going to be our metals, are going to be our cations. And remember, these are going to lose electrons to have that positive charge. Elements in groups 1A, 2A, and 3A are going to lose electrons to have a positive charge equal to their group number. So, for example, sodium is in that group 1A in our alkali metals. It has one valence electron, so it will lose one valence electron to have a positive one charge. So everything in that first column will end up with a positive one charge as an ion. The column next to it, that group 2A, where calcium is, they have two valence electrons. They will lose two electrons to have a positive two charge. So everything in that column will have a positive two charge. That group 3A is on the other side of the transition metals. It has boron at the top, which is kind of a metalloid or non-metal, but then underneath it we have aluminum. So the metals here are going to lose three electrons to have a positive three charge. And that goes for the metals that are in that column. So to name cations, you simply have the element name written as is, and then add ion or cation after it. So like the sodium, the Na plus would simply be a sodium ion or a sodium cation. Calcium would just be a calcium ion. So for metals, we do not actually change the element name. We name the element as is and simply add ion or cation after it. All right, and then our nonmetals, our anions, get to be a little bit more complicated. So remember, anions are the atoms that gain electrons to have a negative charge. These are going to be our nonmetals. And usually elements in groups 8A and group 4A tend to not form ions. So that's where carbon is, and then that is our noble gases. To find the charge of a group A nonmetal, you can subtract 8 from the group number. So like group 7A are halogens. You can do 7 minus 8, and that whole column will have a -1 charge. If you're looking from the right, so noble gases we said would not have a charge, that would be a charge of like 0. The next column would be a -1. The column before that would be a -2. One before that will be -3. And like I said, that group 4A where carbon is tends to not form ions because it can be positive or negative. So you can look at which column the nonmetal is in to find the charge as well. Now, to name the anion name is not identical to the element name. Whenever we name an anion, we take the stem of the element name, so the first part of the element name, chop off the ending, and we change the ending to IDE to show that it's an ion. So like an oxygen ion would have that ox from oxygen and then the ending of IDE, so it would become oxide. Fluorine would chop off the ending and become fluoride. Nitrogen, chop off the ending and become nitride. So cations we named as is. Anions, we chop off the ending and change the ending to IDE. All right, so let's look at putting this together and actually naming binary compounds. So binary compounds, bi means 2. So this is simply made of 2 elements, and we have binary ionic compounds and binary molecular compounds. So we're just going to look at the ionic ones today. So whenever you're naming, always double check and make sure the compound is made of 1 metal and 1 nonmetal. That way you can use your ionic rules. And to name any binary ionic compound, you have the cation named first. So remember the metal named as is, followed by the anion name, where we change the ending to IDE. So for example, if we have CS2O, CS is cesium, so we name that as is. O is oxygen, but in a compound we change it to oxide with that IDE ending. So that would be cesium oxide. Also, for example, we have NaBr. Na is sodium. We name it as is. Br is bromine, so we change the ending to IDE to become bromide. So let's look at these 2 examples together. We have SrF2. Sr is number 38 on the periodic table, so you can locate it. It is strontium. And remember, we named that as is. And then F is fluorine. That's number 9 on the periodic table. That way you can find it. So fluorine, we change the ending to IDE. So that would be strontium fluoride. And that's the name of that compound. Looking at CaCl2, Ca is calcium, which is number 20 on the periodic table. Cl is chlorine, so we would change that to chloride. So that compound's name is cesium chloride. So what tends to be more difficult for people, instead of naming, tends to be writing the formulas, tends to be more difficult. So when we're writing formulas for the binary ionic compounds, if you know the name of an ion, you can write its formula. So its formula is going to be its symbol with its charge for that ion. So we're first going to write the symbol of the cation and then the symbol of the anion. And what we're going to do is we are going to end up adding subscripts to balance the formula, because remember, compounds have an overall neutral charge. So how we can find those subscripts is we can use the crisscross method. So the charge, the number of the cation becomes the subscript of the anion. The charge number of the anion is going to become the subscript of the cation. So you can see this in the picture on the left. You see that the 1 from lithium goes down to be the subscript of oxygen. And you don't have to write the 1 subscript. You can just leave it blank and it's kind of assumed that it's 1. The 2 from oxide now becomes the subscript for lithium. And one thing to note is subscript should be written in the lowest whole number ratio. So it should be a 1-to-1 ratio instead of like a 2-to-2. So if subscripts are divisible by the same number, you need to reduce it. So you can see this from the picture on the right, where we have lead that's a +4 charge, oxide that's a -2. When they crisscross these, we have Pb2O4. Both of those are divisible by 2, so we can reduce them, divide by 2. So our actual formula is going to be PbO2. So let's do a couple examples, and we're not going to do all of these for time's sake. But let's do barium bromide, potassium nitride, calcium nitride, and barium sulfide. We'll do those middle 4. So barium bromide, if you find barium, it is in the second column. It's number 56. Barium is Ba. Since it is in the second column, it does have a +2 charge. Bromide comes from bromine, which is number 35, which has a symbol of Br. And it's in that group 7A, so it has a -1 charge. So remember we said we are going to crisscross our charges. So that means that the 2 from barium is going to go down as the subscript of bromine. And the 1 from bromine comes down as the subscript of barium. So our formula is Ba, and you don't have to write the 1, Br, and we have that 2 subscript for barium. Let's look at the next one, potassium nitride. Potassium is number 19, which is K. It is in the first column, so it has a +1 charge. Nitride comes from nitrogen, which is number 7. It is in group 5A. So if you do the 5 minus 8, it has a -3 charge. And yet again, when we crisscross, the 1 from potassium goes down to nitrogen. The 3 from nitrogen comes down to potassium. So it's going to be K3N. And that balances all of the charges so that it's a neutral compound. And for calcium nitride, calcium is number 20. It is Ca. It is in the second column, so it is a +2 charge. Nitride we just did, it's N, and it's in that group 5A, so it has a -3 charge. So whenever you crisscross, Ca is going to get the 3 as a subscript from the nitride. The nitrogen is going to get the 2 subscript from calcium. Let's look at this last one, barium sulfide. Barium we did up above, it's Ba, and it's in the second column, so it has a +2 charge. Sulfide comes from sulfur, which is S, and it is in group 6A. It has a -2 charge. So when we crisscross, we end up with Ba2S2. Notice that our subscripts, though, are both divisible by 2. So we would have to divide them by 2 to reduce it. So this would just be BAS for our overall compound. And with ionic compounds, we also encounter polyatomic ions. We looked at some of these in our last unit with bonding. These were the things that were covalently bonded and had a charge. So polyatomic ions are a tightly bound group of atoms that behave as a unit and carry a charge. So for example, sulfate is SO4 -2. So it's made of 1 sulfur and 4 oxygens that overall has a -2 charge. There actually is a list of these on the back of your reference sheet. If you turn to the back page where the Bohr diagram was, to the left of the Bohr diagram is a table of common polyatomic ions. The names of most of these, you'll notice, end in either ITE or ATE. And if there's a pair of polyatomic ions that are made up of the same elements, the ITE is going to signal the ion that has less oxygen. So if you look, there's a sulfite and a sulfate. The sulfite is the one that has less oxygen. And we're going to look at how you name things with polyatomic ions. You're never going to change the name of a polyatomic ion. So you would just write the name of that as is. So let's do some examples of compounds that have polyatomic ions. Naming is pretty straightforward. It's just recognizing if there are more than 2 capital letters, you know you have a polyatomic ion in there somewhere. But let's look at writing the formulas for these, because that's the one that's a little more difficult. So we're going to write the formula for the cation and then the formula for the polyatomic ion and crisscross to balance the charges, just like we did anything else. So lithium carbonate, lithium is number 3 on the periodic table. It is Li. It is in the first column, so it has a +1 charge. Carbonate, anytime you see that ITE or ATE, look at your polyatomic list. Carbonate is CO3 with a -2 charge. And just like we did with other ionic compounds, we are going to crisscross. So the 2 from carbonate is going to go down as the subscript from lithium. The 1 from lithium goes down as the subscript for carbonate. Now, that does not change the formula for carbonate. It just tells us that we have 1 carbonate. So we don't do anything to the subscript of that polyatomic. We write it as is. So that is our final formula for lithium carbonate. Let's look at potassium sulfate. This is going to be treated the same way. Potassium is number 19, that is K. It does have a +1 charge. Sulfate, that ATE, you know it's on your polyatomic list, that is SO4 with a -2 charge. So this, when we crisscross, is going to look the same. The 1 from potassium just tells us that we have 1 sulfate, but remember we don't change the subscript. But that means we're going to have 2 potassiums, so it's going to be K2SO4. Where this can be a little bit more difficult is if we should have more than one of those polyatomic ions. So our cation, or whatever that first one that we're using and we're crisscrossing, does not have a charge of 1. So when we're supposed to have more than one of the polyatomic ions, how we signify that is we place parentheses around the polyatomic ion with that subscript on the outside. So to show you what this looks like, let's look at calcium nitrate. Calcium is number 20 on the periodic table. That's Ca. It has a +2 charge. Nitrate, the ATE, you know that's on your polyatomic list. That is NO3, and that has a -1 charge. So whenever we crisscross, calcium gets the 1 from nitrate, so we don't have to write a subscript there. But that 2 from calcium tells us we should have 2 nitrates. If we do not put parentheses and we just put the 2 there, it looks like we have 32 oxygens. So we place that nitrate in parentheses. showing that we have 2 of the nitrate ion altogether. And whenever you are writing these, notice that if it is a capital letter, make sure that we can tell it's capitalized. If it is a lowercase letter in the symbol, make sure we can tell it's lowercase. You cannot just use all capitals or all lowercase. Pay attention to how it is in the symbol as it's given. This next one, ammonium sulfite. Ammonium is your only positive polyatomic ion. It's at the very top of your polyatomic list. It has a formula of NH4 plus, so that means it has a positive 1 charge. And then sulfite, make sure you pick up the right one. Sulfite is SO3 -2. So whenever we crisscross these, the ammonium, the NH4, gets that subscript of 2 from the that should say SO3. I miswrote that. That gets the subscript of 2 from sulfite, and then sulfite, the SO3, gets the subscript of 1 from the ammonium, so we don't have to add anything to it. But I wanted to bring that one up because that's your only positive polyatomic. All of the others are going to be anions. Looking at the next one, magnesium sulfate. So magnesium is number 12 on your periodic table. That's Mg. It's in the second column, so it is a positive 2 charge. Sulfate with the ATE is SO4 with a -2 charge. So whenever we crisscross charges, magnesium is going to get the 2 from sulfate. Sulfate is going to get the 2 from magnesium. Now notice here we crisscrossed over a 2. There are 2 subscripts that are divisible by 2. Now, it cannot be the subscript that is part of the polyatomic ion, but if we have multiples of that polyatomic ion, we can reduce this to just MgSO4. So there will end up being 1 of each of those in that formula. So you can reduce it if the subscript is outside of parentheses, but if it is part of the polyatomic ion, you cannot reduce it. On the flip side, if you are naming the compound, you simply state the cation name first, then the anion name, just as you would for your other ionic compounds. But remember, you are never going to change the name of a polyatomic. So if we had something like KMNO4, notice that there are more than 2 capital letters, so we know there's a polyatomic there. So you can look at your polyatomic list and determine that it's going to split kind of down the middle right there. So we would name K is potassium, so we would name it as is. And then we would look at MnO4 on our polyatomic list is permanganate. So we name it as is and do not change the ending. So you are able to get a head start on your homework and start practicing naming these compounds that have just the metal and the nonmetal, or they contain polyatomic ions. Whenever we get to transition metals, we'll deal with those tomorrow. We do have to add an extra step in there, but I want you to practice with these first before we move on to anything else.